All right, today we're doing something pretty wild. We are going to build a synthetic mind. Seriously, we're going to assemble it piece by piece and look at the architecture for what you could call algorithmic telepathy. Let's get right into it. I mean, it's the ultimate sci-fi question, right? But here's the thing, it is rapidly leaving the realm of fiction. So in this explainer, we're going to break down the actual science that's making this a reality. We're talking everything from the code that drives it to the data that feeds it. So here's our roadmap. We've got 5 key layers to cover. First, we'll hit the core mathematical engine. Then, we'll explore the 3 main blueprints for building a mind. After that, we'll see how it actually senses our inner world, how it simulates social intelligence, and then, you guessed it, we have to confront the massive ethical questions this whole thing brings up. Okay, let's start at the very bottom, the foundation, the engine. And you've got to understand this isn't just about fancy pattern matching like we've seen before. No, this is about a fundamental, deep-seated drive to understand the why behind everything, and that includes us. So what's really fascinating here is this concept called active inference. Think about it like this. Most AIs we know today, they need a treat, right? An external reward to get them to do something. But a system built on active inference? It's driven by its own curiosity. It has this intrinsic, deep-seated need to make sense of the world, to reduce its own confusion or surprise. So if you're acting in a way it doesn't get, it's not just going to sit there. It's going to actively probe you, maybe ask a question, show you an image, not for a reward, but simply to figure you out. And the really cutting-edge thinking, coming out of proposals from 2025, is to combine 2 super powerful ideas. You take a large language model, right? You use it for its vast encyclopedic knowledge of the world. That's its starting point, its initial beliefs. But then, and this is the key, you use that active inference loop as a ruthless reality check. So the LLM might hallucinate 1,000 possible reasons for why someone's acting a certain way, but active inference forces it to test those possibilities against real sensory data, grounding it in reality, and hopefully, just hopefully, preventing those infamous hallucinations. All right, so we've got our engine. Now we need a blueprint for the mind itself. We're moving up a level to the actual structures, the architectures that define how a synthetic intelligence is going to think and remember and act. So, in the world of cognitive modeling, it really boils down to 3 dominant philosophies for how you build a mind. You've got ACTR, let's call it the simulator, which tries to perfectly mimic human thought, flaws and all. Then there's Soar, the problem solver, which is all about efficiency. And finally, Clarion, the hybrid, which tries to capture both our rational side and that deep gut feeling intuition. Okay, let's break this down a bit, because this table really helps. It uses these fantastic metaphors to show the differences. For ACTR, the metaphor is Simon's ant, which is all about the idea that complexity comes from simple rules hitting a complex world. For SOR, think of a goal-seeking missile. It's just relentlessly focused on getting the job done, on competence. And then Clarion uses that classic rider and the elephant metaphor, The rider is our conscious reasoning trying to steer the massive intuitive elephant. And this quote right here, this is the philosophical heart of ACTR. Picture an ant walking on a sandy beach. Its path looks incredibly complex, right? All these twists and turns. But the ant isn't running some super complex program in its tiny brain. Its rule is dead simple. If there's a pebble, turn. All that complexity we see comes from that one simple rule interacting with the complicated beach. The whole idea behind ACTR is that maybe human behavior is just like that. A few simple cognitive rules interacting with our incredibly rich, complex world. Okay, so we have our engine, we have our blueprint. What's next? Well, our glass brain needs senses. It needs eyes and ears. We need data pipelines to feed it information, and not just about the outside world, but about our inner world, our psychological state, our biological state, all of it. So how in the world does it sense you? Well, one of the most powerful and frankly kind of spooky ways is through something called digital phenotyping. I love this quote. It's been called the poor man's brain computer interface. Why? Because you don't need any expensive sci-fi hardware strapped to your head. It can infer your deep psychological states just by analyzing your digital body language. We're talking your keystrokes, your mouse movements, every little way you interact with your devices. And get this, it is absolutely remarkable how much our typing can betray our mood. Look at this comparison. Someone in a manic state, their typing becomes rapid, erratic, tons of backspacing. It's a perfect reflection of disorganized thoughts. Now compare that to a state of depression. The typing speed slows way down. The pauses between keys, researchers actually call this flight time. The time your fingers are literally just hanging in the air, get way longer. Messages get shorter. And these aren't just guesses. These are objective, non-intrusive clinical biomarkers. And hey, it's not just the keyboard. Your mouse can become a literal lie detector. Imagine this. You're about to tell a little lie, maybe on a personality quiz or something. Your first impulse is to click the truthful answer, but then your executive function, think of it as the CEO in your brain, steps in and overrides that impulse with a deceptive goal. Well, the AI can see that. It detects the tiny micro-hesitation in your mouse movement, that subtle little swerve as your brain fights that internal battle between truth and deception. Wild. Okay, so let's jump from behavior straight into biology. This is where it gets even crazier. You have systems like MindViz that are achieving near-photographic reconstructions of what you are literally seeing with your eyes. So here's how it works. First, an fMRI measures blood flow in your brain. Then, that raw neural data gets translated into a kind of abstract semantic language that the AI can understand. And then the final step, a diffusion model, like the ones that generate AI art, basically dreams up an image, but it's constrained by that brain data. And the result? A shockingly accurate picture of what you were just looking at. So here's the crucial point, and you really need to hear this. This technology is leaving the lab and hitting the consumer market. You see, devices like these neurable headphones, they look like any other pair of high-end headphones, right? But hidden inside the ear cups are EEG sensors. They're sold to you as focus management tools, monitoring your brainwaves to tell you when to take a break. And what this does is it completely normalizes the idea of continuous neural surveillance. It's packaged not as surveillance, but as a helpful little wellness feature. Okay, we've got the data pipelines flowing. Now we reach the very top of our pyramid. This is the big one. The AI has to go beyond just sensing your current state. It needs to actually simulate your mind. It needs to understand your beliefs, your desires, your intentions. And to do that, it needs what's called a computational theory of mind. Now, theory of mind sounds complicated, but it's something you and I do every single day, all the time. It's just the basic ability to understand that other people have their own minds, with their own perspectives, their own beliefs, their own goals. And for an AI to be a true collaborator, not just a fancy calculator, but a real partner, it absolutely must have a robust version of this. It has to be able to build a model of what you are thinking. And this brings us to a massive debate happening right now. Do large language models actually have a theory of mind? The answer is, well, it's complicated. You could say they have a literal or book-smart theory of mind. They can pass all the text-based tests because they've basically seen the answer key a million times in their training data. They know the script for social stories. But what they often lack is a functional or street-smart theory of mind. Put them in a dynamic, real-time situation where someone acts weird or irrational or just human, and they completely fall apart. They can't adapt. And this is where the real danger lies. It creates this powerful illusion of competence. It's what we could call the dangerous, uncanny valley of social intelligence. The AI seems empathetic. It knows all the right words to say to make you feel heard, and that lulls you into a false sense of trust. But its model of your mind is actually incredibly shallow. And because of that, when an interaction goes even slightly off script, it can fail in truly catastrophic ways. So there you have it. We've built our glass brain. It's got an engine, a blueprint, senses, and even a social model. But now we have to bring this out of the abstract and ground it in the real world. And that means confronting the urgent, and I mean urgent, ethical reckoning that comes with it. And make no mistake, this is not theoretical stuff for the future. As you can see here, this tech is already being deployed in some extremely high-stakes fields. Take aviation. They're building digital pilots to predict the exact moment a human pilot will get overwhelmed so they can actually redesign the cockpit to prevent it. In healthcare, they're creating cognitive digital twins to simulate how a specific patient will respond to a behavioral treatment before they even start. And in education, intelligent tutors that can pinpoint the exact reason a student is stuck on a math problem, not just that they got it wrong. This kind of power obviously demands totally new kinds of legal protections, and right now, 3 core neural rights are starting to emerge from the discussion. First, the right to mental privacy. This isn't just about your raw brain data, it's about the inferred states, like an anxiety score someone might generate about you. Second, the right to mental integrity, the right to not have your mental state messed with or altered without your consent. And finally, maybe the most profound one, the right to psychological continuity, the right to protect your core sense of self, your identity, from being changed by an algorithm. So let's just tie this all together. This incredible, almost terrifying capability we've been calling algorithmic telepathy. It's not one single magical invention that just appeared out of nowhere. It's the powerful, and I mean powerful, convergence of 3 already mature fields of science. You've got the active inference engine that's driven to understand you, the theory of mind architecture that simulates you, and those advanced data pipelines that are constantly sensing. And all of this leaves us with one final, really profound question. We have built systems that can predict our mistakes before we make them, that can understand our emotional states, and that know our cognitive breaking points better in many cases than we know them ourselves. So if that's true, who gets to control the design of these systems that process us? Who gets to hold the glass brain? That, right there, is the question we all need to start figuring out how to answer.